All right. So we're doing this portion. This portion is going to be more about fluid statics. So static fluid. And one thing we need to know is Navier-Stokes again. So d rho dt plus, I believe, is gradient dot rho v equals 0. As we know, the velocity is not here unless they change, it probably won't be here. But I can see a static question with, no, we can't because density change requires a velocity usually. But either way, this is called the continuity or the mass conservation equation. That portion is gone. We're not really going to care about it. So next portion is this portion. I think we all know this question. I mean, if you don't know, that's fine. Um, remember the negative over here. And this tau can be transformed into, I believe, mu gradient square u plus mu plus lambda parentheses gradient dot v. Either one will do. And then rho g, we know there's no velocity, so all these are gone, and it's supposed to be a v. We know there's no velocity, so for static question, you get something like this. Although, generally speaking, we won't be using this too much right now. This question doesn't look like I might need it. Let's read the question, actually. The specific gravity of seawater is 1.15. Okay, so the SG equals 1.15. What is the absolute pressure at the bottom of the sea? So it is basically just going over here and the specific gravity of the seawater. So then we can just say rho and then rho at 4 equal 1.15. So you can imagine that's 115, I believe, because you're multiplying by 1,000. I believe this is going to be in kilograms per meter cubed. Hopefully I'm correct. If I'm not, then oh well, doesn't really matter. You can figure it out on your own. Right? Yeah. Anyway, the standard atmospheric pressure, um, yeah, let's go to atmospheric pressure because VATM is also needed, um, which is about 101 kilopascals, as we know, or 1 ATM. And then we're looking for, we can use Bernoulli, but I haven't taught you Bernoulli yet, so that's why we haven't really touched it. We could go and do a cross product or a dot product with the top over there with the V equation to create Bernoulli, but we don't need any of that. Please see that as one dimensional. So we can cancel everything out except for negative z direction, let's just say, plus rho gz. So rho p rho z is equal to rho gz h if you're trying to take an integral of that, which equals pressure. And this must be a constant. As you can tell, that must be true at any point. That is a classic equation that we figured out. Um, so with that, actually this would be a z, but we could do a constant minus a constant. So constant over here and a constant over here. We can say the pressure coefficient difference equals to rho gz, and then we can say z2 minus z1 as we claimed last time when we did this. Now, here's the thing. We can do P minus PO equal rho GZ, parentheses Z2 minus Z1, and then we can claim over here, let's just move over here, P equal rho GZ, and let's just make this, let's just make this S for easy access to it, H. So with that H, we can claim easily, right, that it is PO plus this H, basically, or rho GH plus the PO. What's PO? That's 101 kilopascals. So plus whatever 115 is multiplied by 9.8 multiplied by the height difference. The height is 3,000. And this is also have to be multiplied by 1,000. So remember that. Grab your calculator and figure it out. It's really cramped here because of how I didn't set this correctly, but it's fine. It's not going to be a major problem. So I get something. Here's the important part. Let me just grab the something out. Um, okay. Mm, okay. Oh, here it is. Okay, I get. Okay, I need to put the equal sign somewhere. Um, this equals about 3482000. So that is mega. So we can say, ooh, that's interesting. 1, 2, 3, 4, 5, 6, right? Huh. I think I made a mistake in the times table somewhere. Well, we'll figure out that later. But we know it's going to be D because of the first two units. But in my opinion, it should be seven of them to get that effect. So I must have missed a zero in my calculator somewhere, which makes sense. I probably missed it when I did 1.15 multiplied by 1,000. Did I? Yeah, this is an extra zero. So over here has an extra zero. And my apologies. I did not multiply by 1,000 correctly. There we go. So it is D, although. Okay, let me just clean this up and then put D down over here. you might be realizing that I go from first principle a lot, so you'll be seeing a lot of Navier-Stokes here. The specific gravity of mercury is 13.6, and the specific gravity of glycerine is 1.26. For the mammary showing, calculate the difference in pressure between point A and point B. So let's just go to the first principle again. In my opinion, the only way you should teach fluid mechanics go from first principle always. So I always go for first principle. So zero over here, zero over here. So then we go over here to rho. I don't really like how they teach undergrads, although because they don't go from first principle. But I can understand why, because a lot of times you don't need this level of math knowledge on the Navier-Stokes level. Um, if you look at all the mathematics in a real life situation, there's a reason why they differentiate fluid statics and so on and so forth. Because I can kind of see why they wouldn't need it. Because think about it, if it's static, you can just go for rho GH and immediately get the answer, right? So yeah, I understand why they do it. I just don't think that's the right way to teach it. Yeah, but in reality, I also should have done this, in my opinion. In my opinion, I should draw it like this, honestly. And actually, in my opinion, you should write it like this if you're going to write it as a factor notation. And in my opinion, it's just all my opinion, so it's completely your choice to write it like I do. And then what else is there? Plus rho G. Oh yeah, plus rho G. So, in my opinion, you should start from first principles always, which is the Navier-Stokes equation. But I get why they skip this part because think about how annoying it would be to always go to the Navier-Stokes and then just to find out you cancel all these out because this over here, and you have to also teach them tensor notation. I did it with my brother and I figured out why they don't teach it this way, but in my opinion, it's much better if you teach it this way. But anyways, this also is of why we get rid of that is because in the Navier-Stokes equation, rho plus tau parentheses, I believe is v gradient dot v parentheses. This lambda is equal to, I believe, mu bulk plus 2 divided by 3 mu, if you didn't know. So that's kind of how I did over here. Don't get confused. This allows this to have like a 2 mu cofactor and so on and so forth. Either way, we figure out from this a negative gradient pow, parentheses plus rho gz. Again, I always go for first principle, so it makes sense why I showcase this each and every time. And if you're asking, do I get this from memory? Yes, exactly. I just get it from memory because I've used Navier-Stokes so much in my lifetime that it's ingrained in my bone. And the way they talk, even the index notation is ingrained in my bone now. Like I can recite the Navier-Stokes like the back of my head now. Fortunately, or unfortunately, depending on how you look at it. For me, it's fortunately, but for you guys, you don't need that level of shit. Anyway, because actually this actually can be a DZ now because of how it turns out to be. Anyways, for now, you can just write rho P rho Z equals rho G Z, which is equivalent to saying P is equal to rho GZH, as we know, if you take an integral of that, actually Z again, but that Z is equal to a constant. We can do a constant minus constant, as we know, to get to the differential pressure equals rho GZ H instead. Either way, we have done that many times, so I hope we know. Um, Although I will make a contest over here. This over here is not equivalent to saying this. This is not true. Some people get confused by that because they're both triangles. They look the same. No, they're not the same. I realize I should have been more clarifying on that one. So over here, let's now begin this arduous track up. So first of all, we can just cancel all this part out because we know that that's attached to each other. There's no point of me caring for that. Now, there's a point to caring for this one. There's an argument to say, although looking at how different it is, it won't really matter. Now, I'm pretty sure these two are supposed to be attached, same level. I think the picture I took of this probably is horrible, but no, it's fine. It's not really a big deal, I don't think. So we can start with PA, and then we can go down and up from here, however you choose to do it. So let's just think about this for a second. You can go from here to, if this over here is our equilibrium. Now, if you have Bernoulli, you don't have to do any of this shit. Just saying Bernoulli is king for a reason in one of these questions. If this is equilibrium, the H direction, because H is technically a difference and now has it's actually a vector now. The reason why it turns to a vector kind of is it can be a positive or negative direction. So it's a one-dimensional vector now, which is a little weird, but still a vector. Pressure is a scalar. So what does that really mean? What I'm trying to say is that it is a positive, negative, so it's a scalar. Sorry, my apologies, a scalar now. But you can see that the scalar has a direction too. So depending on how you look at it, it does kind of have a momentary like direction, but it doesn't, it's a scalar in the end of the day. A momentary directional scalar, I guess. Whatever. I don't know. I don't know how to describe it too much, but I do. I just described it. What am I saying? Anyway. Rho, let's go water. Oh, wait. Sorry. I want to do something really interesting. I want to say plus, I want to say plus instead, right? Why plus? Because we have negative g from gravity and kind of, and then plus from the direction. It's kind of what my brain thought of. My reality is depend on your reference point, and you can choose positive if you want and negative if you want. Um, but it's your choice ultimately. Okay? Actually, it's really your choice, actually. So in reality, you could have done this instead. You could have just say let's go to this point over here and how to get to there. And we're trying to get to 1, 2, I believe this is not 3, this is 3, and this is 4. So instead of going there, we could just say, let's go to the same point, 2 over here, because 2 is the same thing. And I can say P2, and we can look at the above over here, right? Which is going to have a PB, B from, well, we get the PA over here, and then P2 equal PB over here. So this and this is going to have 3 terms. So you can think about this and say, there's going to be a row water, and there's going to be H difference of 3 comma 4. So 3 comma 4 over here. And then plus low water, mercury, mercury. There's a G over here, low G, and then H of whatever 3 to 2 is. Yeah. And then PB over here. Continue from here. So we're doing PB over here, which is plus 2 low G glycerin, whatever that is, G glycerin. And it's gonna be H2 over here, which I labeled as 2 to 1, or 1 to 2. Now, here's what we're doing over here. We are creating an equilibrium point over here. So everything up is positive. Earlier, we could have done something different, but over here, we're saying equilibrium point is positive. So with that said, we can do minus these, we can subtract these two. We can do this, which is 0 on the bottom, and then say PA minus PB. And you can imagine this, if you keep on going with this, you keep on going with this. Um, so let's just put all the additions first. Rho G, forgot the G, 1 comma 2, and it's gonna be minus rho W G, rho 3 comma 4 plus minus rho M G H2. You can imagine what's gonna happen over here. We are looking for the difference over here, I believe, the difference between point A and B. So you can imagine over here, if you really wanted to look at it, this would be, in a sense, going PA minus PB. We move everything to one other side. We can say this, and we can move the G out, and we can do parentheses over here. So with that being said, it will be negative rho glycerin H1 to 2, right? And let me make sure that's yeah, I think that's correct. And then um did I do this correctly? I hope I did. Minus 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 minus. I think I did this wrong. I think this is supposed to be minus and this is supposed to be plus. My apologies. So this is supposed to be plus because you're moving the other side, and it's gonna be minus rho W H3 comma 4 minus rho M G H2, and you got the bracket in. I think that's right. I think this is 2, 3, although I don't think I put 2, 3. All right, there. Now we have this. There's many ways to do it. The easiest way is Bernoulli, by the way. I am purposely not using Bernoulli, just because we don't know that yet, and we're not derived that yet. I will derive it when we do dynamics, and that's when all the pain comes in. So that when the derivation goes in. But we can also now take out the raw water because we know Sg equals raw water at 4T plus rho. So whatever low thing is, so we can multiply by that. So we can say glycerin is 1.26, right? Instead of, and then we can just multiply 1,000 at the end, and we can get the height of H1 and 2, which is about 0.5, right? And then we can do plus minus, and then rho water is taken out, so we can do 3 and 4, which is over here, I believe. 3 and 4 is this thing. So it's about 0.125 because that's rho water, and minus rho m, wherever rho m is, mercury. Does it give mercury? Ah, yes, it's 13.16. And then we can finally create the H23, which is about this distance over here, which is 1 minus 0.125 parentheses, parentheses. So with that being said, we can just do that math. We grab our calculator and we do 9 point, we probably want to do the inside first because that makes things easier. So plug that into your calculator and then you can get the right answer, hopefully. Depending on what the right answer is, you could, I mean, there's only one right answer, honestly. And then it is 1 minus that parentheses. So, syntax there, I must have made a mistake. 1 minus 0.125, maybe I have to do it separately. All right, 0.725. Okay, inside I got, and multiply by 9.8, multiply by 1,000. Okay, I get about approximately negative 111,671. Okay, so we know that is D. Sorry about the bad explanation. I kept on fumbling my explanation earlier. That's my apologies. But you should get D in the end. D plus the gradient that parentheses rho V equals 0. And we're going to say 0, 0 because this is our mass conservation, which we know there's no velocity. Then we start over here with dv dt plus v dot gradient v parentheses equal negative gradient p plus a gradient dot tau, which we're going to actually showcase over here what this means. This tau can be indicated over here as mu gradient square v plus mu plus lambda parentheses gradient dot v, and then it's going to be plus rho, and then the body force like that. All right, we already know that this is going to be zero because there's no velocity movement, there's no velocity movement here, so we can get gradient p plus rho bv plus some external force if there is any equals zero. So now, is there any external force? Is a good question, yeah. Uh, yeah, so there's a small f over here. It's actually called small f usually. And this is called the exterior force. So we could just call it exterior force for what it is. Because when we take an integral and do a dv like this, the volume integral like this, we can claim by saying, and we move this to the side, we can claim this. I believe we could claim integral of Pn dA equal integral rho, which is going to be g and dv plus f, and that's if I remember correctly, what we're going to indicate over here. And you can kind of see there's a disposition of basically the um, pressure force and the other forces down there. So obviously those are the two forces we really care about. And I will tell you right now, we can instantly figure out what the pressure is going to be by looking at the previous function over here. This with the b with the possible force outside. So what we're going to do, because actually there's no external first, it's actually most likely going to be zero, is what I'm trying to indicate here. But for now, we leave that in. Let me just erase all this because we have solved for it, right? So right now, we're thinking along the lines of something like, well, I think you guys all know it because we did it multiple times, in my opinion, is 0 equal negative gradient p plus rho g in the z direction plus f small. Now, f small is static. There's no way that is going to exert any force, in my opinion, but I could be wrong, right? So let's just leave it for now. Right? No, we can't leave it for now. All we're gonna do is just make it zero. So indicate the integral zero. So that means there's no force on anywhere where we're doing a body force like this. Now, is that true or not? It's a real question, and we'll figure that solution out soon. First, we're gonna do something called d dz p plus equals rho gz, which this indicates that pressure must be rho g z equal constant. Right? Because it's static. It's a very much a non-dynamic question. So we can indicate that over here. So with that being said, we can say that after that, we can say this is equal to saying dF. Like this is the total force now because we figured out that F is nothing. So instead of that, we're integrating this and this is everything now. So that helps a lot. Doesn't it? A little bit? Yeah, I think it does. But with that derivative, we can actually indicate here that if I were to take a derivative of this, you would get, I believe, if I'm correct, uh, f r equal integral of this is f resultant. Uh, let's just call it S or area, or maybe we just keep it the area notation P that dA, which is equal to saying rho g, and then because of this over here, and we can just call it rho gh for simplicity. We can call it integral of a h dA. Why did I say change to h is because of the notation wise in a classic copy and paste method, because a lot of times you just copy and paste the solution in your like final solution. What was it called again? The derivative. There's derivative with the what they called again? Centroid, and that makes it easier. But we're not doing that. We're deriving everything. So that's why we're doing this. But if you were to derive it that way, you wouldn't need all this painful algebra. So this is integral a h dA is what I'm trying to figure out. Now understand that h is over here. So we can say h equal maybe s sine theta, where s is the distance of this distance over here, and h is over here. So we can formulate it differently. So we can formulate it a little bit differently, and we can get the angle too, because the angle is constant, right? So instead of doing all this bananas over here, we can do something like first get the angle, right? So sine of theta is one thing we need to do, and it is 4 over the hypotenuse, so 4 over whatever square root of 5 square plus 4 square is. And with that said, you can grab your calculator, which I don't know where I placed, but I hope I placed it somewhere safe. I did. So with that said, I can grab the calculator and then do division and do 4 divided by the second square root of 5 square plus 4 square. And that gives you a ridiculously interesting number. That gives you 0.624695048. This is probably going to be more interesting than I thought. I thought this would be a more cozy question. I was wrong. This is actually a pretty intense question. Um, if you're asking me why we're going to the integral method when there's an easier method, well, that's my brain went to this way, but there probably is an easier method to solve this, which I know. I'm gonna switch. I'm gonna switch up later, but for now we're gonna follow this method over here. So yeah. Oh, why is it not working now? Okay. So for now we have claimed that it is S. Come on, S, and it's going to be multiplied by 0.6249504.8. So you can kind of indicate here FR equal rho G integral of S. And now why we do S is because S, you can transform the dA into equal to, well, 4ds is what I'm trying to put down over here because um, what's happening here is the width is 4, right? This let's just say BS, and then DS is a little bit of the continuous displacement that we transformed here. So we can take an integral of that, and then we can say 0.624 whatever 95048 multiplied by 4, and then DS. We know that's a polynomial, and now we can figure out the whole answer. So the final solution would be looking like. Now, honestly, would people ever use this method? I have no idea. There's actually easier method. I think I taught it a long time ago, the easier method, but we're gonna do 0 to L. So L is this length over here because ds is over here, the small element over here. And it's gonna be S, and then it's gonna be whatever multiplied by 4 ds. So we can just actually move all the constants out, right? I don't know why it's not doing it carefully. By 0.48 parentheses 4, and then it's gonna be integral S ds basically. And if you solve that question, you would get the answer of that. So let me just grab my calculator and just quickly put that in. So it is 1000 for water, 9.8, and then it's going to be 0.6495 multiplied by 4, and it's going to be bracket s squared divided by 2 on 0 to 6.24 something. So yeah, let me just put that into my calculator. 1000 multiplied by 9.8, multiplied by whatever it was before, multiplied by 4, and then doing a second integral from 0 to square root of 5 square plus 4 square. And then it is x, was it just x dx? Okay, so I get FR equal 502,004.9406. So that is obviously C. The answer was C. Now, this is asking for the vertical force of an inclined wall. We know the resultant force or equals about, I think, 502 kilonewtons. So that is something that we don't know of. We don't know that angle. We have no idea what it is. But we can determine over here that it probably is going to be perpendicular to, the wall, generally speaking. So if we want this, you could do angle over here, which is theta. And we know from that, this is the angle we're looking for. And we're looking for, looks like it's going to be the R vertical equal 502 kilonewtons. And it's going to be cosine whatever angle that is. So 502 divided by square root of whatever 5 square plus 4 square is cosine. So we have to look at 5. And that equals the answer. So we grab our calculators again, and then you do the math again. So 5 square plus 4 square. And you probably get like I got something like 391.996, so about B. I get about B, and that should be the answer for this one. So let me just write B over here. Next one is the horizontal force, similar thing again, but this time in this way, which means you just have to change the top. So 502 multiplied by 4 divided by square root of 5 square plus 4 square instead of the previous should give you whatever you want, whatever you desire. So let me just grab that here. So I got about 3.5 equals force horizontal, which is about B. So you can clearly say that B is the answer over here. So maybe I'll split this into